In this video, I want to look at this system which consists of an input shaft connected through some gearing to an output pulley, which has two masses on it. And what I want to do is determine the equivalent inertia of the system, and I want to derive the model in terms of our angular velocity 1 and T1. Now there's a few assumptions that we're going to make. We're going to ignore the inertias of the shafts and the gears, so anything right here we're going to ignore when we're looking at our equivalent inertia. And we are also told that the gear ratio is 2. That means that we are slowing down how fast our output gear is spinning, and we're increasing the torque on the output. So let's look at calculating the equivalent inertia of this system. So we start by just looking at the kinetic energy. So with the kinetic energy, we look at each of the individual components. So this input shaft right here is going to be 1/2. It's only rotating, so it's only going to have an inertia, I1, and it's rotating with an angular velocity of omega 1. So we're going to have omega 1 squared. Now we're told to ignore this shaft right here, we're told to ignore this gear, we're told to ignore this gear, and we're told to ignore this shaft, and what we're left with is the output pulley. So that again is also only rotating, so we're going to have plus 1/2, this is I2, and this is rotating at omega 2, so omega 2 squared. Now, we have these two masses. These masses aren't rotating. They're just moving up and down. So they're linearly translating, which means their kinetic energy is only going to be plus 1/2 m2v. Well, if this is moving up and this is moving down, they're moving at the same velocity. So I'm just going to call this v right now. So v squared. And then plus 1/2 m3v squared. Now, what we need to do is we need to combine these terms. We need to get rid of our omega, and we need to get rid of these v's. So if we use our gear ratio right here, what we want to do is write this in terms of omega 1. So we want to substitute out this omega 2. So omega 2 is going to be equal to omega 1 over 2. So we'll be able to put that into this equation. Now, how do we substitute out v? Well, v is going to be equal to r, which is the radius of the pulley, times omega. And the pulley is rotating at omega 2 because this shaft and the pulley are rigidly attached to each other. So we're going to have this v is equal to r omega 2. Well, we also know that omega 2 is equal to this omega 1 divided by 2. So v is equal to r omega 1 divided by 2. So we can put that into each of our v's. So let's go ahead and do that and simplify this equation a little bit. So this is going to be equal to 1/2 I1 omega 1 squared. That one doesn't change. Plus 1/2 I2. And omega 2 is going to be omega 1 over 2 squared plus 1/2 m2 times r omega 1 over 2 squared plus 1/2 times m3 times r omega 1 over 2 squared. So let's continue on and just simplify these squared terms. Again, the first one we're not changing anything with, so it just stays the same. But the second term, we're going to have 1/2 I2 times omega 1 squared over 4 plus 1/2 m2. Now each of these terms are squared, so r squared omega 1 squared over 4 plus 1/2 m3 r squared omega 1 squared over 4. Now, we want to collect terms. So each of these terms has a 1/2. So we're going to take a 1/2 out. And now we're going to collect our inertia terms and any coefficients that we have. So we're going to have I1 plus Well, this is going to be 1/4 I2 plus 1/4 M2R2 plus 1/4 M3R R squared. So those are all of my inertia and mass terms. And then I still have my omega 1 squared. So this term right in here is my equivalent inertia. Now, let's go to the next part where we derive the model of the system in terms of omega 1 and T1. Looking at this pulley, what do we see? Well, if we draw a free body diagram, we see two cables. Forgetting about the masses right now, we just have two cables. We'll say this is tension 1 and this is tension 2. Thinking back to our dynamics courses, we would always say that T1 is equal to T2 is equal to some tension, one rope, one tension. But that's because we were always ignoring the mass and the inertia of the pulley. So we would say mass is equal to 0 or our inertia is equal to 0. And that would pretty much give us the moment equation of, if we look at I times our angular acceleration is equal to the sum of the moment. If our mass is equal to 0 or our inertia is equal to 0, this side of the equation is going to be 0. And let's just say that this has a radius of r. We'll see it doesn't matter in a minute, but we'll see that this is minus t1 times r plus t2 times r is equal to 0. The r's can get divided out, and what we get T1 is equal to T2. Based on the assumptions we were making that the pulley is massless or the pulley has no inertia. Well, when we're told that the pulley has some inertia right here, so this equation, we can't make this assumption. So we see that the tension on each side of this pulley is going to be different, and we're going to leave it as T1 and T2 for right now. Now, when we go and we try to figure out the equation of motion of the system, we are still going to use the sum of my moments are going to be equal to my equivalent inertia times, what am I looking for? Omega 1. So in terms of my angular acceleration is going to be omega dot. Now, we still have this pulley system, so we need to figure out what this input shaft sees. Well, this input shaft, and let's say this is a positive way that we're counterclockwise is positive. Our input shaft is going to be T1. That's the torque on the input shaft. And then it's going to have the masses. So this is going to have T1. Going down is going to be M2G. On this other side is going to be T2. And going down is going to be M3G. So we know that tension 1 is going to be equal to M2G. Tension 2 is going to be equal to M3G just from summing our forces in the Y. And, well, we need to adjust it just a little bit. So when we adjust it, we have to remember that since we're using a gear, the torque, really, we need to divide out the gear ratio. So when we look at this, it's going to be minus M2G, right? So this T1, it's going to be minus M2G times R divided by this gear ratio, which is 2. And then this other one is going to be plus M3GR over 2. Again, this 2 is because this output is, this gear ratio right here is doubling the torque. It's reducing the speed by half and it's doubling the torque. So our input shaft is only going to see half that torque. So then we have our equivalent inertia, which is 1e I1 plus 1/4 I2 plus 1/4 m2r squared plus, let's move this over just a little bit, plus 1/4 m3 r squared, and we have omega 1 dot. So this right here is the equation of motion that we have. So we have the sum of our moments. Again, T1 comes from the torque that the input shaft sees. T2, or these two terms right here, come from the pulley, summing the moments on the pulley and realizing that the pulley has some mass and some inertia, so its tensions are not the same. And this term right here is our equivalent inertia, i.e., which we solved for in the first part. So hopefully this video has helped you understand how we can derive an equation of motion of a system that has some rotating and translational parts.